Stars are luminous spheres of plasma held together by their own gravity. They fill our night sky, and are an essential element in our survival on Earth. But where do they come from? Our journey into the life of the star begins with a gas cloud. A gas cloud is a mixture of gas, plasma and dust. Electromagnetic radiation from these clouds tells us that they usually contain an abundance of mainly ionized hydrogen and helium, but other elements and their ions can also be found in particularly hot clouds. Gas clouds contain two important forces: kinetic energy, which causes the cloud to expand, and gravitational potential energy, which causes the cloud to contract. These forces balance in equilibrium. For a star to be born, the equilibrium must be shattered, and the cloud must begin to collapse. Small clouds require an agitating force to cause the cloud to collapse, such as the passing by of nearby stars or the radiation from a supernova. But large clouds may begin to collapse under their own gravity, fragmenting and forming dense clusters of gas that will slowly collapse into protostars. During this time, the cloud is called a stellar nursery. Fragments of gas continue to collapse into dense spheres, causing them to heat up. These balls of hot gas can be seen using infrared imaging and are called protostars. Protostars will live for millions of years before igniting, and during this time they must channel their heat by ejecting a stream of gas from both poles. If it fails to do this, the heat will repel the matter required to reach ignition. This process of channeling heat is called bipolar outflow, and is seen on the infrared images of these soon-to-be stars. Once the temperature of a protostar exceeds 10 million Kelvin, hydrogen begins to fuse, and the star is born. Now able to stabilize, it becomes a main sequence star. Main sequence stars fuse hydrogen into helium within their cores. The outward pressure produced by the fusion balances the inward pressure of the star's gravity, keeping it stable. About 90% of the stars in the known universe are main sequence stars. These stars can range from about 1/10 of the mass of the Sun up to 200 times as massive. A star is only main sequence as long as there is hydrogen in its core. Once it has all been fused, it leaves the main sequence. The more massive a star is, the faster the fusion happens. For this reason, larger stars have a shorter main sequence life. Here is the Hertzsprung-Russell diagram. It shows us how a star will live and die depending on its size. There are three paths that a star can follow. The smallest stars will follow this path along the main sequence as they stop fusing. This is the path to a white dwarf. The stars here will fork off upwards, expanding into red giants. These collapse into white dwarfs. Our Sun is now 4.6 billion years old, and will eventually follow this path, beginning to expand in about 6 billion years. Larger stars branch off earlier and become supergiants. These massive stars eventually collapse into a supernova explosion, but more on that later. Stars up to 8 times as massive as our Sun collapse into white dwarfs. White dwarfs no longer perform fusion at their cores. They remain so hot that it will take longer than the current life of the universe to cool down. They will burn forever. To form a white dwarf, all of the hydrogen within its core will burn up, causing gravity to take over and compress the star. As this happens, the temperature increases, enabling helium to fuse with carbon. This produces huge amounts of energy, and causes the star to expand to a massive size. They appear to be bright red due to the core burning brighter than the hydrogen shell. As the core continues to collapse, the smaller stars will end their life as a white dwarf. However, the bigger, more massive stars expand larger as they run out of helium, into the supergiants of space. It is in this stage that the biggest stars in the universe reach their greatest size. Elements even heavier than carbon and oxygen can fuse in these cores. The pressure and heat eventually causing a huge explosion, releasing incredible amounts of energy. From here, a supernova is born. As all the smaller stars have collapsed into white dwarfs, a planetary nebulae is formed. As the red giant collapses, it releases its outer shell, sending vast amounts of gas and dust into space. Illuminated by the white dwarfs at its centre, the nebula glows with bright colours. Contrary to the name, a planetary nebula has nothing to do with planets, and the gas and dust will eventually be swept and dispersed into space. Supernovas are massive explosions that can briefly outshine a galaxy and radiate more energy than our Sun will in its entire lifetime. During a supernova, a star ejects most of its mass into space. Light can be seen for weeks or even months after the initial explosion. This amazing event marks the death of a star, and at its heart lies the headstone, a neutron star. A neutron star is the size of a city, but so dense that a lump of neutron star, the size of a teaspoon, would weigh 10 billion tons here on Earth. Neutron stars are created when the energy of a supernova causes protons and electrons to fuse together in the core, creating neutrons. These neutrons are packed tightly within a sphere only 20 kilometers in width. Because of their density, neutron stars have a gravity 2 billion times stronger than gravity on Earth, and due to the supernova that created them, they can spin 43,000 times per minute, gradually slowing over time. However, if a star has too much mass and keeps collapsing inwards, something even more sinister is formed: a black hole. Scientifically known as a singularity in space and time, black holes mark the boundary of modern science. Their gravity is so strong that anything within the event horizon cannot escape it, even light. This makes black holes observable only by the absence of light. And this marks the end of the star's life. The journey from simple clouds of gas to massive supergiant monsters, leading to the black holes, and the end of our cycle. But it's not quite the end yet. Cycles go round. Recently, a white dwarf has been seen to release carbon from within its core, allowing some hydrogen that was trapped in the outer shell to be pulled into its core, reigniting itself, as it once more fuses hydrogen and emits a brighter light than before. Some astronomers had theorized these events, but they expected it to take hundreds of years. We now know that this process can happen in less than a decade. which is equivalent to seconds in the length of the lifetime of a star. White dwarfs aren't the only ones to be brought back to life. The debris scattered by dying stars helps to provide fuel for the new ones, and the shockwaves from a supernova can play an important role in triggering the birth of another star. In this vast universe, it is the death of one star that enables the life of another.